Good evening, epidemiologists. This is the webinar that precedes Class 3, and the topic is bias and confounding. My name is still Joanne Wilkinson, and in a minute we're going to talk about the plan for tonight's webcast. So we're going to talk tonight about, confounding and this other thing called effect modification, which I'll explain the difference between the two and give examples. We'll talk briefly about how to control for confounding and effect modification using statistics. Although next class, when we do biostatistics, we'll talk about it in more detail. And then we'll talk about bias. There's different types of bias in study design. We'll list them and go over them and use examples to review how they can affect study results. And then we'll do a brief review at the end of causation and critical appraisal of articles, which is what we'll be doing in class probably tomorrow. I don't know how far in advance you're listening to this, but next class we'll do that. So confounding is this: when you want to study the relationship between one thing and another thing, but there's a third variable that's related to both things, but it's not in the causal pathway. In other words, if you're looking at, say, the relationship between exercise and the development of coronary artery disease, it's not, so it would be in the causal pathway, for example, if you said that people who exercise more develop lower percent body fat, and lower percent body fat is associated with development of CAD. That's the causal pathway. However, not in the causal pathway, it's likely that people who exercise are also more likely to follow a healthier diet, and that is also related to coronary artery disease, but it's not caused by the exercise. It just happens to be related. So a confounder is a variable that is disproportionately found in one group or another, and probably also affects the outcome. So for example, the class study that we've done, we want to know whether the region that you're from is associated with your preferred specialty choice in medical school. And believe me, I know there's a lot of things wrong with this study, like that's why I made it that way, so we'll talk about all the flaws in it. But say that's the question. So our hypothesis, whether right or wrong, is that students from the Northeast are less likely to choose primary care specialties. This happens to be an area that I know something about because one of my roles in the medical school is to try to get more people to go into primary care, although you should in no way view this survey as an attempt to make you do that. I just happen to know a little bit about the topic. So our theory is that students from the Northeast perhaps are more likely to be exposed to subspecialty care growing up because there's so many doctors here, and they associate subspecialty care with being smart and having an interesting job, and so they think it's more fun and they want to do that. But what if it's true, for example, say that students from the Northeast are on average younger? They're more likely to go straight from college to medical school, whereas students from other parts of the country are more likely to have done something else in the meantime. That may or may not be true, but suppose it's true. And what if it's true that younger students are less likely to choose primary care? And people with more life experience, the other way to say it is people with more life experience are more likely to choose a primary care specialty. So in that case, age could potentially confound the relationship between the Northeast and not going into primary care. So here's an at-home exercise that you can do. Just take a minute to jot this down. You have not only your class study to look at, but there's also an article assigned that has to do with specialty choice in medical school. So list all the factors that you think might be associated with specialty choice in medical school, whether you think gender or age or region or socioeconomic status or race, ethnicity, or how old you are or whatever might be associated. Just make a whole list of all the things that you think might be there. And then look at those factors again and put a star next to those that might also have to do with what region you grew up in. Some of them I would not expect them to be. For example, there's no reason to think that BU takes more women from the Northeast than they take from the West Coast, right? But some of those factors may actually have to do a little bit with region. And then make two lists. The starred factors that were measured in this study, because we asked some demographic questions, but we didn't ask them all, and make another list of those that were not. The ones that were measured are your measured confounders, and you can deal with those in the analysis because you know what they are. The other ones are your unmeasured confounders, and they are a bigger problem because they may cause bias in your study results, which we'll talk about later, and you can't do anything about it because you didn't measure them. So the important rule is, as you're planning a study, you should think about potential confounders, and if at all possible, you should try to measure them. So here's how we deal with confounding. If you have measured potential confounders, which is a good thing, then you can adjust for them in the statistical analysis. So, for example, if you want to look at the effect of region on specialty preference, but you think age is a potential confounder, then you do two analyses. You do what's called a crude estimate of the relationship between region and specialty preference without the confounder in there, just to see what the odds ratio is. And then you do an adjusted estimate, which takes age into account. And the adjusted estimate basically says, if you could hold the age of the two groups, Northeast and non-Northeast, constant, then after you did that, would there still be a difference? And this is usually the way to do the adjusted estimate is via multiple logistic regression, which we'll talk about next time. But I'm going to show you an example in a moment, just so you can sort of see what the numbers would look like. So again, I don't expect you to be able to do this for this class, but you will see how to do it in the biostats lecture. Here is a crude analysis. I totally made up these numbers because I don't know what the numbers in our study are going to be. Excuse me, I have a cold. So we're looking at students from the Northeast, not from the Northeast, right? Primary care, people who choose primary care, people who choose a subspecialty. And yes, I know that you haven't chosen yet. We're just asking what you think you want to do now, which is one of the flaws of the study, but we'll get back to that later. So the odds ratio, as you recall, is A times D over B times C, or 30 times 35 over 40 times 70, and when you do it all out, it's 0.375. In other words, students from the Northeast are 0.38 times as likely to go into primary care as students not from the Northeast, so they're less likely. But hey, so you notice that of the 100 students from the Northeast, 80 of them are under age 24. In other words, they pretty much went straight to medical school from college. While of the non-Northeast students, only 20 of them are under age 24. And I totally made this up. I don't know what the numbers are really going to look like. And I doubt that there would be that big an age difference just because admissions is kind of random. But just bear with me for the example. So for the adjusted analysis, what we would do is we would say, what does region all by itself have? What's the effect that it has on the odds of choosing primary care? And then what's the odds ratio that age has? And as you can see, age has a much bigger effect than region. I also threw gender in there just because we usually put more than two variables in the adjusted analysis. And so you can see that once you take out age and gender, region, people from the Northeast have 0.95 times the likelihood of choosing a primary care specialty, and the 95% confidence interval crosses 1, which we'll talk about in the next lecture, means that it's not statistically significant. So basically, if you had not also looked at age, you might be fooled into thinking that the region was important in specialty choice, whereas really it's age. The region is just a red herring because there happen to be a lot of young people in the Northeast. Effect modification, or interaction, as some people call it, is not the same thing as confounding, but I think it's actually more interesting. It's when there's a third variable that doesn't change the main relationship as a confounder does, but the main relationship or effect is modified in that group. So for example, going back again to cholesterol-lowering drugs and prevention of coronary artery disease, taking cholesterol-lowering drugs or statins lowers your risk of CAD in everyone, but it lowers it more in men. So say that the odds ratio for men taking statins is 0.2, meaning men who take statins are 0.2 times as likely to get coronary disease as men who do not take statins, and for women it's 0.8. So they're still less likely to get CAD, but the effect is modified in men and women, and it probably has to do with hormones and other things. So here's an example, just with raw numbers in it. This is an effect modification table. You'll see that the result is MI or no MI, or coronary disease, no coronary disease. And then the first two rows are taking statin male, not taking statin male. And then the second two rows, you can think about it as even a separate table, is taking statin female, not taking statin female. And each group has 500 in it. And you can see here that you can even just see looking at the raw numbers, right, that the impact of taking a statin is greater in men. So the odds ratio for men is 10 times 450 over 50 times 490, or 0.18. Basically, you can round it to 0.2. The odds ratio for women is 20 times 475 divided by 20 times 480, and that is 0.79. You can round it to 0.8. So basically, this is effect modification because the effect of taking statins is modified by gender. It is the same effect in both genders, but it is a lot more in one gender than the other, and that is very common. So moving on to bias. There are two kinds of potential error in a research study. Error means the findings of your study do not actually accurately reflect true phenomena. For example, you find that taking statins does not reduce the risk of MI, even though in real life it does. So there's two reasons that your study could screw up that way. The first kind is random error. Just you cannot do anything about random error. If you do the same experiment 100 times, you'll get somewhat different results. And one time, you might find the opposite result than what is true. And that is just random statistical error. And that's why we have the 0.05 p-value to tell you whether your results are statistically significant. And we'll talk about that more in the next lecture. But the other kind of error is bias. And bias happens when there's something about your study design that leads you to a result that's not accurate. For example, if we conducted the previously mentioned study about region of the country and specialty choice, we might get different results if we did it after a full year of ICM versus at the beginning of the school year. We might get different results if we did it after third year as opposed to the beginning of the school year. And probably the results would be more accurate. Originally, I had the in-class survey was going to be about stress in medical school, and there was some concern that even filling out the survey would make you all more stressed, so I decided not to do it. But the bias that I had introduced into that was if you're doing a survey that has to do with how stressed out you are about exams, and you administer it the first week of school in September, that's going to be different than if you administered it during an exam week in February or March, right? People are obviously more stressed and they're more likely to answer the questions differently during that time. So there's several different types of bias that I'm going to go over. And the ones I picked to go over for this lecture are the most common types. There are like gazillion kinds of bias, so you may have heard of other kinds that we don't talk about here. So just one thing to say about bias is there's nothing you can do about it once your study has been designed and data collected. You can't adjust for it like you can with confounders. You can't deal with it in the analysis. You simply have to frame or talk about the results of your study knowing what kinds of bias might be there. So it's still really valuable to know about ahead of time because it casts your results in a certain light, and it limits the way you can talk about the generalizability of your results. And there's two kinds of bias. Bias toward the null is bias that would lead your study toward a neutral finding. In other words, it would make it more likely that you would find that there's no association between your exposure and your outcome. Bias away from the null is bias that would lead you to find an association where there might be none. Bias towards the null is obviously better because if you have bias towards the null in your study and you find a positive result, you can say, well, we found that statins are associated with reduction in risk of heart attack. And this is particularly significant because our study was, if anything, biased towards the null. So the fact that we found something means that there really has to be something there. Usually, in thinking about potential bias, you can sort of tell ahead of time whether your bias is more likely to be towards the null or away. Obviously, you never know for sure. So this is the kind of thing where more experienced researchers and more experienced statisticians that know the body of literature better and they know prior studies better can help you figure out what direction your bias is likely to be in. All right, so there's a million different kinds of bias, and we're going to talk about maybe about 8 or 9 kinds, and they're all up there. Sampling or selection bias is when the way that subjects are recruited or selected for a study results in a biased sample. And usually the way that it happens is that certain demographics are over or underrepresented. So for example, we talked about the firecracker thing in the previous webcast in firecrackers and development of VSD. So again, if your control is drawn from an Air Force base where there's a lot of loud noises, I don't know if there are a lot of loud noises on Air Force bases, but I imagine that there are. That could be a problem. Very common problem, posting only flyers in English to recruit subjects for study at BMC, where many of our patients, probably about half, are non-English speaking, is going to result in a biased sample. Recruiting subjects for a study about hormone replacement therapy at a doctor's office. Well, then you're not getting all the patients that don't go to the doctor, right? So think about your own examples. There's many that you could think of, and almost every study that you read potentially has sampling bias, and so it's important to think about that. Think about our class study. What was the selection bias in our class study? We can talk about this tomorrow, but I assume that not everyone in the entire first-year class filled it out. And so the question is, are the people who didn't fill it out different somehow than the people who filled it out? Randomization bias only applies if you have a randomized controlled trial, but when you're going to randomize subjects to receive intervention or control, the method with which you do that randomization can unwittingly bias the outcome. So the one that they always say is like, don't do every other day or the day of the week randomization. Pretty much people always use a random number generator. So this is kind of a theoretical example. But for example, in the statins and CAD study, if you randomize all patients enrolled on a Monday to be in the intervention group, so they get statins, and the Tuesday patients are in the control group, that seems fine at first. That seems like a good idea. But what if that clinic has a certain doctor that only works Mondays, and he's a marathon runner, and he has a lot of these really fit patients that exercise, and they want to go to him because they get the running thing and all that? Well, that totally messes up your results, right? Because exercise also affects the risk of CAD, and so now you have randomization bias. Interviewer bias. This happens a lot. If you are using a live human being to interview your subjects in a study, then that person has the potential to bias the results or what people say in the interview in a couple of different ways. One is that they might actually just go off the reservation and inject some of their personal opinions into the interview, which is not a good idea, obviously, but it could happen. More subtly, though, they might just connect more easily with certain types of patients like them, for example, and they might get more data from them, or they might get more honest answers from them. And even more subtly, and most common, is that they might just produce reactions in the subjects by virtue of their cultural background or their personal appearance that would make the subjects more or less comfortable speaking to them. For example, if you were going to ask patients in urban Roxbury and Dorchester about drug use, and you sent a very sweet, young, white college student female out there to speak to them, you might imagine that some of the men in the study, or any of the subjects really, might feel like, I can't tell this girl that I did cocaine because she'll just be too shocked, right? Whereas if the person you sent out to collect data was like a recovered addict himself and had worked in the area and knew the population really well, he might be more likely to get honest answers. So the solution for this, if there is one, is to try to recruit research assistants who are kind of from the community that you're interviewing in, that will put your subjects at ease, and try to use the same ones throughout, and also adhere rigorously to a protocol. So don't let them go off the script and ask other questions. So here's an example for our class study. So you know that I'm a family physician, right? I assume you know that. So what if the data had been collected in person and not online? And what if the interviewer was me? And I sat you down and said, gee, what specialty do you think you're interested in? Now, some of you might still say ENT, right? But some of the people who are kind of on the fence might say, well, maybe primary care, I don't know. So here's the question, though. What if the interviewer were a surgeon? Would you have answered maybe a little bit differently? Would some of you have been more likely to flip and say, well, I don't know, surgery's kind of cool too? So, the question is, how does the specialty of the interviewer potentially bias some of your answers? Recall bias is basically any phenomenon that causes the subject's recollection of what happened to be inaccurate in any way. So when you're asking people to look back into the past at exposures they had or things they did, one problem is just chronology. The subject recalls the timing of events incorrectly. That has to do with sometimes the way they're asked. There's entire courses in survey design that you can do about memory and how people recall things and how they're related to events and stuff. It's all very interesting. But basically you have to ask the question the same way every time. And the other is the big problem often in surveys is this social desirability phenomenon where the subject is prompted to answer a certain way to look good. For example, how much do you drink? How much do you smoke? Do you have unsafe sex, etc. So in our study, the social desirability question was the question about what's your favorite class in first year so far? And I'm sure that when we look at the results, not that many people are going to say EPH. But if you were at all tempted to say EPH because you were in EPH, that's social desirability bias. Loss to follow-up is a big problem. So in every study, subjects drop out, move away, they die, whatever. The longer the follow-up period, the more people are lost to follow-up. Generally, once someone is lost, you can't use their results. This, again, is an argument for using person time, like we talked about in the last webcast, because then you can use the time that they were there, at least. But if it causes bias, if subjects in certain groups drop out at higher rates for reasons related to the study question. And the classic example is smoking cessation studies. So if you do a study where you have a bunch of smokers, and some of them get a smoking cessation intervention and some of them don't get it, and then a bunch of people, and some people stop smoking, right? People will drop out of the study at the 6-month and 12-month follow-up in higher numbers if they went back to smoking in the interim and they feel kind of bad about it. And so the question is, if a lot of those people in the intervention group quit, but then they went back to smoking later, but then they dropped out of the study, and you don't know that they went back to smoking, will that make it look like your intervention was better than it really was? Because it produced short-term results, but long-term, your results were lost to follow-up. Fidelity of the trial. So this is the idea that whatever the study is doing, whether it's an intervention or data collection, it has to be done exactly the same way every time. And if not, the results can be biased. So for example, if the intervention is a new surgical procedure versus an old one, but all the new procedures are done by the same surgeon and he's just better than the other surgeon, that's a problem. Another issue is, if you're looking at a retrospective cohort study and you're collecting data from a large population of menopausal women who took hormone replacement therapy and you're asking them about diet, and you ask some of them, how many fruits and vegetables do you eat per week? And you ask some of them, how many fruits do you eat every day and which ones? And how many vegetables do you eat every day and which ones? In other words, if the wording of the two questions is different, that may produce different recall. Misclassification of exposure is when the exposure variable, whatever it is collected or classified in such a way that can lead to it being wrong in some subjects. So let's go back to the firecracker study, which is ridiculous, of course, but easy to conceptualize, I think. The question is, what does exposure to firecrackers mean? Does it mean you saw them? Does it mean you heard them? Does it mean you have to hear and see them? Do you have to be outside? How many times is it? Is it all through the pregnancy or just third trimester? So you have to figure out what you mean by exposure to firecrackers, and then you have to ask the question in a simple enough and clear enough way that everyone will understand it the same. So in our class study, the exposure was region of the country. So the question is, what does that mean? I mean, I asked the question fairly generally, but one of the questions I have is, did you understand it as, where were you born? Where did you grow up? Where did you go to high school? Where did you go to college? Where did you live right before you came to medical school? Like, how did you understand that question? And so there's lots of opportunities for misclassification of exposure with the way that I wrote that question. Misclassification of outcome is the same issue, but with the outcome variable. So in the VSD study, the outcome was having a VSD, which seems pretty clear-cut. Either you do or you don't. But how do you measure that? Who says that they have a VSD? Do the cardiologist, the primary care doctor? Do they have to have an echocardiogram, which is the diagnostic test for a VSD? And this is the real one. How long does it need to persist? So many newborns have a VSD transiently, but it closes. If it closes on day 3 of life, does it count? Do they have to have it for a month in order for it to count? You have to decide that up front. And then you have to collect the data the same way for everyone in the study. In our study, the outcome of interest was specialty preference. So how are we defining or measuring that? Are you lumping all the primary care specialties together? Are you lumping the specialties into person-centered and technique-centered? Or, there's some articles that have done that. And then we're asking people during halfway through first year what they think they want to go into. Like, would it be better to ask them later? Would it be better to see what they matched in? Whatever. But we have to ask it the same way every time. And a bonus question. This is a little bit of a sort of a biased question with your study. Why do you think the question was asked about what day of the week are you answering the test? We could talk about that in class. So the bottom line about bias is that you should design your study to minimize bias, but there's always going to be some. It's better to know what it is. Better the bias you know than the bias you don't know. Bias towards the null is better, and you can usually figure out whether it's going to be that or not. You cannot do anything about it in the data analysis phase. But you have to explain it and use it to sort of think about your results. If you don't talk about it, then when you send your article to the journal, the reviewers are going to talk about it. So better that you know it ahead of time. It's all about spin and damage control. So causation, this is the last thing we're going to talk about, and we'll talk about this in class. Several things have to line up to make a case for causation. In other words, we have definitively shown in our study that the exposure causes the outcome. It's always safer to say that the exposure is associated with the outcome, but in some cases, you can get closer to say that it causes the outcome. So you have to have a temporal relationship. You have to have the exposure before the outcome. It has to be biologically or scientifically plausible. Consistency is helpful, so you have to show the association over several different studies, better yet, several different types of studies. The strength, of association, so the size of the odds ratio or rate ratio, if it's bigger, that's more helpful. Dose-response relationship, so if taking statins reduces your risk of CAD, does taking a higher dose of statins reduce your risk more? That's helpful. Reversibility, so if you take people off statins, do they start having heart attacks again? And then the type of study design. In general, randomized controlled trials are considered to be the best. And so here's how, just thinking a little bit about critically appraising the evidence, because we're going to talk about a few articles in class and sort of whether they're good or not. And we'll talk later about meta-analyses and pre-digested sources like UpToDate, because they're sort of a little bit different. But for a primary source like an RCT or a cohort study, what was the question? And really the subtext is, do I care about the question? Did they consider the previous literature when they came up with their question? And was it a new question that hadn't been answered previously by other studies? What was the study design? And was it a good study design for the question that was asked? We'll talk about that more in class. Who was in the study? Were the participants in the study like my patients? Are the methods clear? The standard I usually use is, can I and my fellows understand the methods by reading them in the paper? How were the data presented? Again, is it clear what they did? And then what was the result? Was it statistically significant? Was it clinically significant? Was there potential bias? And if so, what kind? So we'll be looking at several articles in class over the next couple of classes, looking at sort of how well constructed they were, whether there might have been bias, and whether we think that they're sort of good source or not. If you have questions, as always, you can email me. Don't call me from a British telephone booth, but email me instead. Thank you.